Welcome back to another episode of Dominic Does DIY. Thanks for subscribing if you have, and if you haven't, please click the subscribe button and the bell icon to get notified of new videos. Today we'll be reviewing a lithium-ion battery protection circuit. We need to ensure a few types of protections when handling lithium cells. One, we need to make sure that we have overvoltage protection. During charge, we do not want the battery to go over the specified rated voltage of the cell. This is an absolute maximum and can result in fire explosion if we exceed it. Two, we need to take care of over-discharge protection. During operation, we don't want the cell to drop below the absolute cell minimum voltage. If a lithium pack drops below this value, it is considered a bad cell and should be disposed of. Also, when a battery is too low, we should not be attempting a full charge rate, but rather a trickle charge until it reaches a certain voltage, and then at that point we can go to the full charge rate. This can be found specified in the data sheet of the cell you're using. The third thing we need to look out for is thermal protection. Lithium batteries are required to charge and discharge at certain temperatures. This is a chemistry issue. So look at the spec sheet for any abnormalities on it. But for the most part, lithium cells, they have two charge rates. One is between 0 to 10 C, in which you're doing about a 0.1 C charge rate, and 10 to 60 C, which is a full charge rate capability. Outside of the range of 0 and 60, you should not charge. You shouldn't charge below 0 and you shouldn't charge above 60 degrees C. The cold temperatures, these are the more pertinent ones to pay attention to, because these are the temperatures that when you're charging at a low charge rate, you can cause dendrites or things to be built up within the cell itself, which can cause shorts. This is why you can see the 0 to 10 charge rate is usually 0.1 of the full charge rate capability. And then once you're above 10 C, though, you can go full blast. Now, even though I'm going to show you this circuit, most of the time you can find the comparator aspect of this inside a battery protection IC that handles this for you. And then all you would have to really add is that battery protection IC, some capacitors and resistors, and then the two control FETs on the output. But instead of using the battery protection IC, we're going to make our own with some comparators. Now, if you buy one of those pouch cells off of Amazon or wherever, usually they have the battery protection circuit built in. If you see one of those pouch cells and it has a PCBA on it with some wires coming off of it, that's actually the battery protection circuit. So it has one level of protection built in. But if your lithium cell is just that, it's just the cell with some wires coming off of it or some tabs, then that one doesn't have the protection and you need to add it. Or if instead of using pouch cells, you're using cylindrical cells like 18650s, 21700s, or some other cylinder lithium cell, then those do not come with battery protection circuits at all, and you'll have to add those into your circuit. Either this circuit that we're showing here, or like I said, you can go out and take a look at some battery protection ICs that kind of do this for you, minus the FETs and stuff. You still need to add those. So let's get into this and look at the circuit and see how it operates, then run some simulations. So just a quick overview of this, we can see that this thing has some remnants of some earlier videos that I've done. We can see that it has two comparators with some hysteresis built into it. And we can see we have one comparator for our overvoltage protection, and we have one comparator with some hysteresis for our over-discharge protection. The output of those comparators then go into some N-channel MOSFETs. And the N-channel MOSFETs, quick look, it kind of looks like they're just two NFETs in an AND gate arrangement, but this is not necessarily true. When we look at it closer, we can see that the overvoltage protection FET, it is actually backwards. So instead of the source going to ground, we actually have the drain going to ground and the source connecting to the P- line. The reason this is done is because during a shutdown state, either OVP or ODP, you do not want to impede the other function. So during charge, if we went into OVP mode, you still want the system to be able to discharge. And likewise, if you go into over discharge protection and the battery is low, you still want to be able to charge the cell. So when one of the protection FETs engages, the other action will still function by passing current through the body diode of the FET that is turned off, allowing current to only flow in one direction. I chose for the design to have an OVP set to 4.23 volts and the ODP set to 2.5 volts. Of course, this is just reference for now, and we can manipulate as needed later after we run the simulations. During an earlier video, I spoke about comparators and hysteresis, and I made a spreadsheet to do all these calculations for me that I used to get the 12K and the 4K feedback resistor with the 330 input resistance. So if you want a link to that spreadsheet, just let me know in a comment down below, and I'll go ahead and link it. The reason we want hysteresis is because when you turn the charge off, the battery voltage is going to drop by some value based on the charge rate and the cell's internal resistance. And we don't want to restart the charger just because the battery relaxes a little bit. So we need that hysteresis, so it has to go down enough that we actually know that the battery has discharged. Now looking at the full system schematic here, we can see that the actual battery is connected to the same location as V1. However, the system, whatever we're trying to power, is not directly connected to the battery. The system positive and negative is denoted by P plus and P minus, whereas the battery is B plus and B minus. For the simulation, I put R5 in as a 1 ohm resistor. However, in application, that component would actually be a properly rated fuse for your system. We will run two simulations. One, where we are in discharge mode and simulating the battery going from 4.5 volts down to 2.0 volts. And then a second simulation where we are in charge mode, where we will see the battery go from 2.0 volts to 4.5 volts. So we will first go to discharge mode and we will monitor current through our load R3 and OVP versus the battery voltage. So the simulation I ran was a DC sweep on V1. And so on our x-axis, we can see our discharge going from 4.5 volts on the left all the way over to 2.0 volts on the right. So the top plot, this is our OVP comparator output. The second plot is our ODP comparator output. And the third plot is the actual current through our load resistor R3. So long as the battery voltage is greater than the OVP reset voltage, the output of the comparator is going to be 0. And that is going to cause M1 to be in an off state. But the system can still discharge because it is discharging through the body diode of that OVP FET. As soon as the battery voltage drops below the reset voltage, the OVP comparator output goes high, turning the FET on, and now we have an increase of voltage drop across our load, which is seen through the increased current through R3. So you can see when the OVP line goes high, we have an increased current on R3. As we continue to discharge the cell, meaning going to the right on the graphs, we can see at around 2.5 volts, which is our ODP value, the current through the load drops to 0. This is because the cell dropped below our desired operating levels. So we can see our battery protection circuit works for over discharge protection. Now let's look at the charger side. First thing for charge, I added the charge source V3. This represents like a USB-C charger or something like that. This is very rudimentary. You'd actually have a charger IC, which would be outputting like a CCCV charger, but for this, I'm just using a voltage source, and the charge current will be set by R5, which is that 1 ohm resistor. So the charge rate will just be 5 minus my battery voltage, since the resistor is 1. That's just Ohm's law. So when we ran it, we get the same plots, except instead of monitoring R3, we're going to monitor the current through V1, which is the battery charge rate. Now these three plots, they look very similar to the discharge, just inverse. Remember, in the discharge, I was going from 4.5 volts down to 2, but now because I'm charging, my battery is dead, so I'm starting my battery voltage at 2.0 volts and going up to 4.5 volts. So just like during discharge, as long as our battery is below our ODP reset trip point of 2.9 volts, the system still charges, but at a reduced rate. As soon as the ODP resets, meaning we get above that 2.9 volts threshold, the current increases due to the reduced line impedance, since M2 is now on and it doesn't have to drop voltage across the body diode of the FET. Once the battery is charged to the OVP value of 4.23 volts over here, we can see the current through the battery drops to 0 just as expected. So the OVP circuit checks out and is working as expected. Now this circuit has the following properties. Our OVP trip point is 4.23 volts. Our OVP reset point is 4.11 volts. Our ODP trip point is 2.5 volts, and our ODP reset point is 2.9 volts. So those windows are some pretty good windows for our application with these trip points. So we've taken care of the over voltage protection. We've taken care of the over discharge protection. So the third protection that we needed to take care of was the thermal protection. And for this, we actually need to monitor the cell temp, not ambient. This isn't a do not charge in ambient temperatures, but actually we should be monitoring the cell temperature. Now, depending on your application, depending on the cell, your ambient may be very, very close to your cell temp, so you might be able to get away with it. But you primarily want to try to focus on getting the cell temperature. Now, because this involves an NTC and like it's 2 circuits in one, and I've exhausted enough of your time so far, I will save that for another video. Actually, if you want to see that video of how to do the thermal hardware solution rather than just do an easy mode, which is you use a voltage divider into a microcontroller and its ADC port, let me know in the comments down below. And that's it for today's episode. I hope you enjoyed it, and if you did, share it with some friends. I'm getting some stuff in the mail, so the plan is to make something for the next video. Until next time, keep on keeping on.